Before anything we know existed, before stars, before galaxies, before even time as we understand it, the universe was in a state that defies human imagination. Everything that would one day become space, matter, energy, and physical law was once compressed into a condition of extreme density and heat. There was no direction, no distance, no light in the way we define it today. The universe did not expand into space because space itself was not yet fully formed. Instead, space and time emerged together from an event that scientists describe as the Big Bang. This was not an explosion in a location. It was the rapid expansion of all space everywhere at once, marking the beginning of everything we can observe and everything we are still trying to understand. In the earliest fraction of a second, the universe existed in an almost incomprehensible state. Temperatures were so extreme that no atoms could exist, not even protons or neutrons. The fundamental forces that govern reality today were likely unified into a single force. Gravity, electromagnetism, and the nuclear forces were not separate entities, but different expressions of one underlying principle that we have not yet fully discovered. As the universe expanded and cooled, this unity began to break apart, allowing the first distinctions between forces to appear. This separation set the stage for everything that followed, including the formation of matter itself. One of the most important and mysterious periods in this early history is known as cosmic inflation. During this phase, the universe is believed to have expanded at an extraordinary rate, far faster than the speed of light. This does not violate the laws of physics, because it was space itself expanding, not objects moving through space. In an incredibly short amount of time, smaller than a trillionth of a second, the universe grew from something subatomic in scale to something far larger than we can easily conceptualize. This rapid expansion smoothed out the structure of the early cosmos, distributing energy and matter in a way that later allowed galaxies to form. As inflation ended, the universe continued to expand, but at a slower rate. Energy began to convert into particles, giving rise to the first building blocks of matter. Quarks, electrons, and neutrinos emerged from a hot, dense soup of energy. Quarks combined to form protons and neutrons, and in the following minutes, the first simple atomic nuclei began to form in a process known as nucleosynthesis. Hydrogen and helium were the dominant elements created during this time, along with trace amounts of lithium. These were the seeds of all future stars, planets, and ultimately, life itself. For hundreds of thousands of years, the universe remained a hot plasma of charged particles. Light could not travel freely because it constantly interacted with this dense environment, scattering in every direction. The universe at this stage was opaque, filled with a glowing fog of energy. It was not until the universe expanded and cooled enough for electrons to combine with atomic nuclei that neutral atoms could form. This moment, known as recombination, allowed light to travel freely for the first time. That ancient light still exists today as the cosmic microwave background radiation, a faint glow that fills the entire universe and serves as one of the most important pieces of evidence for the Big Bang theory. As the universe continued to evolve, regions of slightly higher density began to collapse under the influence of gravity. Over immense periods of time, these regions grew into the first stars. These early stars were vastly different from those we see today. They were massive, short-lived, and composed almost entirely of hydrogen and helium. Their intense gravitational pressure ignited nuclear fusion in their cores, producing light and energy. These first stars played a crucial role in shaping the universe by forging heavier elements through nuclear reactions in their cores. When these early stars reached the end of their lives, many of them exploded in powerful supernova events. These explosions scattered heavy elements such as carbon, oxygen, and iron into space. These elements became the raw material for new generations of stars, planets, and eventually life. Without these stellar processes, the universe would have remained a simple place composed mostly of hydrogen and helium. Instead, it became rich and diverse, capable of producing complex chemistry and structure. Over billions of years, gravity continued to shape the universe on the largest scales. Stars gathered into galaxies, galaxies formed clusters, and clusters formed the cosmic web that stretches across the observable universe. This structure is not random. It is shaped by the distribution of dark matter, an invisible form of matter that does not emit or absorb light, but exerts gravitational influence. Although we cannot see dark matter directly, its effects are clearly observed in the motion of galaxies and the way large structures form. It acts as a cosmic scaffold, guiding the formation of visible matter. Even as the universe expanded and evolved, new mysteries began to emerge. One of the most profound is the realization that the expansion of the universe is not slowing down as once expected. Instead, it is accelerating. This acceleration is attributed to a mysterious force known as dark energy. Unlike dark matter, which pulls structures together through gravity, dark energy appears to push the universe apart. Its nature remains one of the greatest unanswered questions in modern physics. It dominates the total energy content of the universe, yet we have almost no direct understanding of what it is. The story of the universe is not just a sequence of events, but a continuous unfolding of complexity from simplicity. From a state of pure energy, the cosmos developed structure, order, and diversity. Every atom in our bodies was once forged in the heart of a star or created in the aftermath of a cosmic explosion. This connection between human existence and the earliest moments of the universe reveals a profound truth. We are not separate from the cosmos. We are a product of its history. As we look deeper into space, we are also looking back in time. Light from distant galaxies takes billions of years to reach us, meaning we see those objects not as they are today, but as they were in the distant past. In this way, the universe acts like a natural time machine. Every observation provides a glimpse into a different era of cosmic history, allowing us to reconstruct the story of everything from the beginning to the present moment. Yet despite all we have learned, the earliest moments of the universe remain hidden behind a veil of uncertainty. The laws of physics as we know them break down under the extreme conditions of the Big Bang. To truly understand what happened at the very beginning, we may need a new theory that unites quantum mechanics and gravity into a single framework. This theory of quantum gravity is one of the greatest goals in modern physics. It may reveal whether the universe had a true beginning or if it is part of a larger, more complex cycle that extends beyond our current understanding. The origin of the universe is not just a scientific question, it is also a philosophical one. It challenges our understanding of existence itself. If time began with the Big Bang, then asking what came before may not have a meaningful answer. Instead, the universe may represent a self-contained system where time and space emerge together without a prior cause in the traditional sense. This idea reshapes how we think about reality and our place within it. Even today, the universe continues to expand, evolve, and change. New stars are born in distant galaxies, while others end their lives in spectacular explosions. Black holes grow by consuming matter and merging with one another, releasing enormous amounts of energy in the process. Galaxies drift apart as space itself stretches between them. The universe is not static. It is dynamic, alive, with processes that operate on scales far beyond human experience. In the end, the story of the universe is also the story of discovery. Every generation of scientists builds upon the knowledge of the past, pushing the boundaries of what we know and what we can imagine. From the first observations of distant galaxies to the detection of cosmic background radiation and gravitational waves, each breakthrough brings us closer to understanding the origin of everything. Yet, with every answer, new questions appear, reminding us that the universe is far from fully understood. What began as a simple expansion of space has become a vast and intricate cosmos filled with mystery, structure, and beauty. The journey from the earliest moment of existence to the present day is a story written across billions of years and trillions of stars. It is a story that continues to unfold, and we are only beginning to read its first chapters. In the earliest moments after the universe came into existence, something extraordinary is believed to have happened, something so extreme that it reshapes our understanding of space, time, and reality itself. This event is known as cosmic inflation. It describes a period when the universe expanded at an unimaginable rate, growing far faster than the speed of light. Not because objects were moving through space, but because space itself was stretching and increasing in scale everywhere at once. This idea does not simply modify our picture of the early universe, it completely transforms it, offering answers to some of the deepest questions about why the universe looks the way it does today. To understand why cosmic inflation is such a powerful concept, it is important to begin with the problems it was created to solve. When scientists first studied the structure of the universe on the largest scales, they discovered something puzzling. The universe appears remarkably uniform in all directions. No matter where we look in the sky, distant regions of space have almost the same temperature, the same overall distribution of matter, and similar large-scale properties. This uniformity should not exist if the universe expanded at a steady rate from the beginning, because regions on opposite sides of the observable universe would never have had enough time to interact or exchange information. There simply would not have been enough time for them to reach thermal equilibrium. This puzzle is known as the horizon problem. It raises a fundamental question. How can two regions of the universe that are so far apart and seemingly disconnected have such similar properties? The standard model of early cosmic expansion could not explain this. Another issue, known as the flatness problem, added to the mystery. Measurements show that the universe is very close to geometrically flat on large scales. This means that parallel lines remain parallel over vast distances, and the overall curvature of space is extremely small. For this to be the case, the initial conditions of the universe would have had to be incredibly fine-tuned. Even a tiny deviation in the early density of the universe would have led to a very different cosmic structure today, either collapsing back on itself or expanding too quickly for galaxies to form. Cosmic inflation was proposed as a solution to these problems. The idea suggests that in the first fraction of a second after the Big Bang, the universe underwent a brief but extremely rapid expansion. During this period, space itself expanded exponentially, smoothing out any irregularities and stretching the fabric of the universe to such a degree that any initial curvature or unevenness became almost undetectable. In this way, regions that are now far apart were once close enough to interact, allowing them to reach the same temperature and physical conditions before being rapidly separated by inflation. The concept of inflation was first developed in the early 1980s as physicists attempted to reconcile the inconsistencies in the standard Big Bang model. It was not originally based on direct observation, but rather on mathematical reasoning and theoretical consistency. Over time, however, evidence began to accumulate that strongly supports its validity. One of the most important pieces of evidence comes from the cosmic microwave background radiation, the faint afterglow of the early universe. Detailed measurements of this radiation reveal tiny fluctuations in temperature and density that match the predictions of inflationary theory with remarkable precision. These tiny fluctuations are not random noise. They represent the seeds of all future structure in the universe. Slight differences in density allowed gravity to gradually pull matter together, forming the first stars, galaxies, and clusters of galaxies. Without these small variations, the universe would have remained a smooth, featureless sea of particles with no structure or complexity. Inflation provides a natural explanation for how these fluctuations originated. It suggests that quantum fluctuations, which are normally confined to microscopic scales, were stretched to cosmic proportions during the rapid expansion of space. Quantum physics plays a crucial role in this picture. On the smallest scales, the universe is not smooth or continuous, but filled with random fluctuations in energy. These fluctuations are usually insignificant at large scales, but during inflation, the rapid expansion of space magnified them dramatically. What began as tiny quantum variations became the blueprint for galaxies and cosmic structures billions of years later. This connection between the smallest and largest scales in nature is one of the most profound ideas in modern cosmology. The mechanism that drove inflation is still not fully understood. Most models suggest the existence of a hypothetical field known as the inflaton field. This field would have filled the early universe, containing a large amount of potential energy. As long as this field remained in a high-energy state, it would have caused space to expand at an exponential rate. Eventually, the field would decay into normal particles and radiation, ending the inflationary period and allowing the universe to transition into the more gradual expansion we observe today. However, the exact nature of this field remains unknown, and no direct evidence of its existence has yet been found. Despite these uncertainties, inflation provides an elegant explanation for several key features of the universe. It explains why the universe appears so uniform on large scales, why it is so close to geometrically flat, and why the distribution of matter shows the specific pattern of fluctuations observed in the cosmic microwave background. It also provides a framework for understanding how large-scale structure emerged from quantum randomness, linking the physics of the very small with the evolution of the very large. One of the most fascinating consequences of inflation is that it suggests the observable universe may be only a small part of a much larger reality. Because inflation would have expanded space so rapidly, regions of the universe that are far beyond our observable horizon may exist with completely different conditions. Some versions of inflationary theory even suggest that inflation may not have ended everywhere at the same time, leading to the possibility of a multiverse, a vast collection of separate universes, each with its own physical properties and laws. While this idea is highly speculative, it arises naturally from some mathematical models of inflation. The idea of a multiverse challenges traditional notions of what the universe means. Instead of being a single, self-contained entity, reality could consist of an enormous number of separate regions, each inflated from its own initial conditions. In some of these regions, the laws of physics might be slightly different, leading to universes that are completely unlike our own. This raises profound questions about the nature of existence and whether our universe is unique or just one of many possible outcomes of a deeper underlying process. Even within our own universe, inflation leaves behind subtle signatures that scientists continue to study. One of the most important predictions is the existence of gravitational waves generated during the inflationary period. These waves are ripples in the fabric of space-time itself, created by the rapid expansion of the early universe. Detecting these primordial gravitational waves would provide direct evidence of inflation and offer a glimpse into the universe at its earliest moments. Although there have been promising observations, the search is still ongoing and remains one of the major goals of modern cosmology. Another important aspect of inflation is how it connects to the concept of entropy and the arrow of time. The universe began in a highly ordered state, which is somewhat counterintuitive, because systems tend to move from order to disorder over time. Inflation helps explain this by suggesting that the early universe was driven into a smooth, low-entropy state through rapid expansion. As inflation ended and matter began to clump together under gravity, entropy increased, leading to the complex structures we see today. This transition from a smooth early universe to a structured cosmic web is one of the key processes that shaped everything from galaxies to planets. Inflation also helps explain why there is more matter than antimatter in the universe. In theory, the Big Bang should have produced equal amounts of both, which would have annihilated each other completely, leaving behind only energy. However, the universe we observe is overwhelmingly made of matter. Some versions of inflationary theory incorporate processes that could have created a slight imbalance between matter and antimatter during the early expansion, allowing matter to dominate after annihilation events. Despite its success in explaining many features of the universe, inflation is not without challenges. One of the main criticisms is that it relies on unknown physics, particularly the inflaton field, which has never been directly observed. Some scientists argue that alternative explanations may eventually replace or modify inflation. Others suggest that inflation is part of a deeper theory that we have not yet discovered, possibly connected to quantum gravity or string theory. The true nature of the early universe may involve principles that go beyond our current understanding of space, time, and energy. What makes inflation so compelling is not just its ability to solve existing problems, but its predictive power. It provides a framework that connects microscopic quantum processes with the large-scale structure of the universe. It transforms the early universe from a chaotic, incomprehensible state into a system governed by physical laws that produce predictable outcomes. At the same time, it opens the door to even greater mysteries, suggesting that our universe may be part of a much larger and more complex reality. As scientists continue to study the cosmic microwave background, gravitational waves, and the distribution of galaxies, they are searching for deeper evidence that can confirm or refine the theory of inflation. Each new observation brings us closer to understanding whether this rapid expansion truly occurred or whether an entirely different mechanism shaped the early universe. The answers to these questions will not only reveal the history of the cosmos, but may also redefine our understanding of reality itself. In the end, cosmic inflation represents one of the most powerful ideas in modern science. It connects the smallest scales of quantum physics with the largest structures in the universe. It explains why the universe is structured the way it is, while also pointing toward mysteries that remain unsolved. Whether inflation is the final answer or just a step toward a deeper theory, it has already changed the way we think about the origin and evolution of everything that exists. In the vast darkness of space, there are objects so extreme that they challenge every known law of physics and stretch the limits of human imagination. These are black holes, regions where gravity becomes so powerful that nothing, not even light, can escape once it crosses a boundary known as the event horizon. Black holes are not empty voids, as their name might suggest. Instead, they are among the most concentrated forms of matter and energy in the universe, created when massive stars collapse under their own gravity, or when enormous amounts of matter are compressed into an incredibly small space. They represent the final stage in the life of some of the most massive objects in the cosmos, and they are also key players in shaping galaxies and cosmic evolution. The story of a black hole often begins with a star. Stars exist in a delicate balance between two opposing forces. On one side is gravity, which constantly tries to pull the star inward, compressing its mass into a smaller and smaller volume. On the other side is the pressure generated by nuclear fusion in the star's core, where hydrogen atoms are fused into helium, releasing enormous amounts of energy. This outward pressure keeps the star stable for most of its life, allowing it to shine for billions of years. However, this balance cannot last forever. Eventually, the star runs out of nuclear fuel. When the fuel in the core is exhausted, nuclear fusion slows and eventually stops. Without the outward pressure generated by fusion, gravity takes over. The core of the star begins to collapse inward, while the outer layers may be expelled in a violent explosion known as a supernova. This explosion can briefly outshine an entire galaxy and scatter heavy elements into space. What remains after the explosion depends on the original mass of the star. For stars with relatively low mass, the result is a dense object called a white dwarf. For more massive stars, the collapse continues further, leading to the formation of a neutron star. But for the most massive stars, there is no known force that can stop the collapse. The core continues to shrink indefinitely, eventually forming a black hole. As the core collapses, it becomes increasingly dense. The gravitational field grows stronger and stronger, warping the fabric of space and time around it. According to Einstein's theory of general relativity, gravity is not just a force, but a curvature of space-time caused by mass and energy. As the mass of the collapsing core becomes concentrated into an ever smaller volume, the curvature of space-time becomes extreme. At a certain point, the escape velocity required to break free from the gravitational pull exceeds the speed of light. This boundary marks the event horizon of a black hole. Once anything crosses this boundary, it can never return. Inside the event horizon, the laws of physics as we know them begin to break down. All paths lead inward toward a central point known as the singularity. At the singularity, density becomes infinite, and space-time curvature becomes extreme. Our current understanding of physics cannot fully describe what happens at this point. It is a place where general relativity and quantum mechanics both fail to provide a complete picture. This makes the singularity one of the greatest mysteries in modern science. Despite being invisible, black holes can be detected through their effects on nearby matter. When gas, dust, or even entire stars come close to a black hole, they can be pulled into orbit around it. This material forms a rotating disk known as an accretion disk. As the matter spirals inward, it is heated to extremely high temperatures due to friction and gravitational compression. This causes the accretion disk to emit intense radiation, including X-rays, which can be detected by telescopes. In some cases, black holes also produce powerful jets of particles that are launched at nearly the speed of light from their poles. These jets can extend for thousands of light years, influencing the environment of entire galaxies. Black holes come in different sizes. Stellar black holes form from the collapse of individual stars and typically have masses ranging from a few to several tens of times the mass of our Sunday. There are also much larger black holes known as supermassive black holes, which exist at the centers of most galaxies, including our own Milky Way. These giants can have masses equivalent to millions or even billions of suns. How they form is still an open question, but it is believed that they grow over time by consuming matter and merging with other black holes. There is also evidence for intermediate mass black holes, which fall between stellar and supermassive black holes, although they are more difficult to detect. The supermassive black hole at the center of the Milky Way is known as Sagittarius A star. It has a mass of about 4 million times that of the Sun and exerts a powerful gravitational influence on the stars and gas in its vicinity. Observations of stars orbiting this invisible object provide strong evidence for its existence. By tracking the motion of these stars over many years, scientists have been able to map the gravitational field and confirm that a compact, extremely massive object lies at the center of our galaxy. One of the most fascinating aspects of black holes is how they affect time. According to general relativity, time passes more slowly in stronger gravitational fields. This means that as an object approaches a black hole, time for that object appears to slow down relative to an outside observer. At the event horizon, time appears to stop completely from the perspective of an external observer. However, from the perspective of the object falling in, time continues normally until it reaches the singularity. This strange difference in the flow of time highlights the extreme nature of black holes and the way they distort reality itself. Black holes also play a crucial role in the evolution of galaxies. The energy released by matter falling into supermassive black holes can influence star formation and regulate the growth of galaxies. In some cases, black holes can release enough energy to push gas out of a galaxy, preventing new stars from forming. This feedback process helps shape the structure and evolution of galaxies over billions of years. Without black holes, galaxies might look very different from what we observe today. In recent years, one of the most significant breakthroughs in astrophysics has been the direct detection of gravitational waves. These waves are ripples in space-time produced by the acceleration of massive objects, such as two black holes orbiting each other and eventually merging. When two black holes collide, they release enormous amounts of energy in the form of gravitational waves, briefly outshining all the stars in the observable universe combined. In 2015, scientists made the first direct detection of gravitational waves, confirming a major prediction of Einstein's theory and opening a new way of observing the universe. This discovery allowed us to witness black hole mergers for the first time, giving us a completely new window into the cosmos. Black hole mergers are among the most violent events in the universe. As two black holes spiral toward each other, they lose energy through gravitational radiation, causing them to move closer together. In the final moments before collision, they orbit each other at a significant fraction of the speed of light. When they finally merge, they form a single, larger black hole, releasing a burst of gravitational waves that travels across the universe. These events provide valuable information about the properties of black holes, including their masses and spins. Another important discovery in black hole physics is the idea that black holes are not completely black. In the 1970s, physicist Stephen Hawking proposed that black holes can emit radiation due to quantum effects near the event horizon. This phenomenon, known as Hawking radiation, suggests that black holes can slowly lose mass over time and eventually evaporate completely. This idea connects quantum mechanics with general relativity and raises deep questions about the nature of information in the universe. If a black hole eventually evaporates, what happens to the information about the objects that fell into it? This is known as the black hole information paradox and remains one of the most important unsolved problems in theoretical physics. Black holes also challenge our understanding of space itself. Inside the event horizon, all directions lead toward the singularity, meaning that space behaves in ways that are completely different from our everyday experience. Some theories suggest that the singularity might not be a point of infinite density, but rather a transition to another state of space-time that we do not yet understand. There are even speculative ideas that black holes could be connected to other regions of the universe, or even other universes entirely, through structures known as wormholes, although there is currently no evidence for this. Despite their extreme nature, black holes are not just cosmic destroyers. They are also essential components of the universe. They help regulate the growth of galaxies, influence the distribution of matter, and provide laboratories for testing the laws of physics under the most extreme conditions. By studying black holes, scientists hope to uncover deeper truths about gravity, quantum mechanics, and the fundamental structure of reality. As our technology improves, we are beginning to observe black holes in greater detail than ever before. The first image of a black hole's event horizon was captured by the Event Horizon Telescope, revealing the shadow of a black hole surrounded by a glowing ring of hot gas. This image provided direct visual evidence of black holes and confirmed long-standing theoretical predictions. It marked a new era in astrophysics, where black holes are no longer just mathematical concepts, but observable objects. Even with all we have learned, black holes remain some of the most mysterious objects in the universe. They represent the limits of our understanding, where the known laws of physics break down and new theories are needed. They connect the largest scales of cosmic structure with the smallest scales of quantum mechanics, suggesting that a deeper theory of reality may be waiting to be discovered. In the end, black holes are not just regions of darkness. They are gateways to some of the most profound questions in science. They challenge our understanding of space, time, and existence itself. As we continue to explore them, they may hold the key to unifying the laws of physics and revealing the true nature of the universe. After the violent death of a massive star, the universe does not always end in a black hole. In some cases, the collapse of a stellar core produces an object so strange and extreme that it defies ordinary understanding of matter. These objects are known as neutron stars, and among them are some of the most precise and powerful natural clocks in the universe, called pulsars. They are born in the aftermath of supernova explosions. When the outer layers of a dying star are blasted into space and the core is crushed under its own gravity until matter reaches a state unlike anything found anywhere else in nature. To understand how a neutron star forms, we must return to the final stages of a massive star's life. When a star significantly larger than our Sun exhausts its nuclear fuel, the balance between outward pressure from fusion and inward pull of gravity collapses. The core begins to contract rapidly. In less massive stars, electron degeneracy pressure can stop the collapse, forming a white dwarf. But in stars above a certain threshold, even this resistance is not enough. The core continues to shrink, and protons and electrons are forced together under immense pressure. In this extreme environment, they combine to form neutrons and neutrinos in a process called inverse beta decay. The neutrinos escape into space, carrying away energy, while the neutrons pack tightly together, forming a dense object made almost entirely of nuclear matter. The result is a neutron star, an object with a mass greater than that of our Sun, compressed into a sphere only about 20 kilometers across. To imagine this density, consider that a teaspoon of neutron star material would weigh billions of tons on Earth. The atoms that once made up the star no longer exist in their usual form. Electrons have been crushed into protons, and the structure of matter has been fundamentally transformed. The result is a giant atomic nucleus held together not by chemical forces, but by the strong nuclear force on a macroscopic scale. The surface of a neutron star is unlike anything we experience in everyday life. It is incredibly smooth on a large scale, but composed of exotic states of matter beneath. The gravity at the surface is so strong that mountains, if they could exist at all, would be only millimeters high before collapsing under their own weight. If a human could somehow stand on a neutron star without being destroyed by radiation or tidal forces, they would be crushed instantly by the immense gravitational pull. The escape velocity from a neutron star is a significant fraction of the speed of light, meaning that anything falling onto its surface releases enormous amounts of energy. One of the most remarkable features of neutron stars is their magnetic fields. These fields are among the strongest known in the universe, trillions of times stronger than Earth's magnetic field. The origin of these extreme fields lies in the collapse of the star itself. As the core shrinks, its magnetic field lines are compressed, increasing their intensity dramatically. In some neutron stars, these magnetic fields become so powerful that they are classified as magnetars. Magnetars can produce bursts of gamma rays and X-rays so intense that they can affect space across vast distances. Neutron stars also rotate at extraordinary speeds. When the original star collapses, its rotation rate increases due to the conservation of angular momentum, much like a spinning figure skater pulling in their arms. Some neutron stars rotate hundreds of times per second. This rapid rotation, combined with their strong magnetic fields, creates beams of electromagnetic radiation that sweep across space like lighthouse beams. When these beams point toward Earth, we observe them as regular pulses of radiation. These are known as pulsars. The discovery of pulsars in 1967 was one of the most surprising events in modern astronomy. The first pulsar was detected by Jocelyn Bell Burnell and Anthony Hewish while they were studying radio signals from space. They noticed a series of extremely regular pulses repeating at precise intervals. At first, the signals were so unusual that they jokingly referred to them as possibly coming from intelligent extraterrestrial life. The signals were so consistent that they seemed artificial. However, further study revealed that they were coming from a rapidly rotating neutron star emitting beams of radio waves. Pulsars are among the most precise natural timekeepers in the universe. Some rotate with such stability that their timing rivals atomic clocks on Earth. This precision allows scientists to use pulsars as cosmic tools for studying a wide range of phenomena. By observing slight variations in their pulse timing, researchers can detect the presence of planets, measure gravitational waves, and study the structure of space-time itself. The mechanism behind pulsar emission is deeply connected to their magnetic fields and rotation. The magnetic axis of a neutron star is usually not aligned with its rotational axis. As the star spins, charged particles are accelerated along the magnetic field lines near the poles. These particles emit radiation in narrow beams. As the star rotates, these beams sweep through space. If Earth lies in the path of these beams, we observe regular pulses of radiation, similar to the flash of a lighthouse seen from a distant shore. There are different types of pulsars depending on their properties and environments. Some are isolated neutron stars that rotate steadily in space. Others are part of binary systems where they orbit another star. In these systems, the neutron star can pull material from its companion, forming an accretion disk, similar to those found around black holes. As this material falls onto the neutron star, it can spin the star up to even higher speeds, creating what are known as millisecond pulsars. These are the fastest known rotating neutron stars in the universe. The study of pulsars has led to some of the most important discoveries in astrophysics. One of the earliest breakthroughs came from observations of a binary pulsar system discovered by Russell Hulse and Joseph Taylor in the 1970s. By carefully tracking the timing of the pulsar's pulses, they noticed that its orbit was gradually shrinking. This could only be explained by the emission of energy in the form of gravitational waves, a phenomenon predicted by Einstein's theory of general relativity, but not directly observed at the time. This indirect detection of gravitational waves provided strong evidence for the theory and eventually led to the first direct detection decades later. Neutron stars also provide a unique laboratory for studying matter under extreme conditions. The density inside a neutron star is so high that atomic nuclei are packed together in ways that cannot be replicated on Earth. Scientists are still trying to understand exactly what happens in the core of a neutron star. Some theories suggest that the matter may break down into even more fundamental particles, such as quarks, forming a state known as quark matter or strange matter. If this is true, neutron stars may contain some of the most exotic forms of matter in the universe. The internal structure of a neutron star is thought to consist of several layers. The outer crust is composed of heavy atomic nuclei arranged in a crystalline lattice. Beneath this lies a layer of superfluid neutrons, where particles move without friction. Deeper still, the matter becomes increasingly dense and may transition into exotic phases that are not yet fully understood. At the very core, the conditions are so extreme that current physics cannot reliably describe what exists. Neutron stars also play an important role in the production of heavy elements in the universe. When two neutron stars collide in a violent event known as a kilonova, they release enormous amounts of energy and eject matter into space. These collisions are believed to be responsible for creating many of the heaviest elements in the periodic table, including gold, platinum, and uranium. The gravitational waves detected from such collisions provide direct evidence of these processes and show that neutron star mergers are one of the key sources of chemical complexity in the universe. The collision of neutron stars is one of the most energetic events in the cosmos. As two dense objects spiral toward each other, They emit gravitational waves that carry away energy and cause them to merge. When they finally collide, the result is a dramatic explosion that can briefly outshine entire galaxies. The material ejected from the collision expands into space, enriching it with heavy elements that later become part of planets, asteroids, and even life itself. In this sense, neutron stars are not just remnants of dead stars, but also creators of new cosmic material. Pulsars and neutron stars also allow scientists to test the limits of fundamental physics. Because their conditions are so extreme, they provide natural laboratories for studying gravity, magnetism, and quantum mechanics in ways that cannot be replicated on Earth. By observing how light and matter behave near these objects, researchers can test Einstein's theory of general relativity with extraordinary precision. Any deviation from predicted behavior could point to new physics beyond our current understanding. Some neutron stars exist in environments where they are slowly being consumed by black holes. In such cases, the neutron star is gradually torn apart by tidal forces as it spirals inward. This process releases enormous amounts of energy and produces gravitational waves that carry information about both objects. These events help scientists study the relationship between neutron stars and black holes and understand how extreme gravity behaves in different contexts. Despite their small size, neutron stars have a profound influence on the universe. They are responsible for some of the most energetic phenomena known, including gamma-ray bursts, which are brief but extremely powerful flashes of high-energy radiation observed in distant galaxies. These bursts are thought to be associated with the formation of black holes or the collision of neutron stars. Their energy output can outshine entire galaxies for a short period of time. As technology advances, our ability to study neutron stars continues to improve. Radio telescopes, X-ray observatories, and gravitational wave detectors all contribute to a more complete understanding of these objects. Each new observation reveals more about their structure, behavior, and role in the cosmos. Yet, many questions remain unanswered. The exact nature of matter at the core of a neutron star is still unknown. The origin of their magnetic fields and the full range of their evolutionary paths are still active areas of research. Neutron stars and pulsars represent one of the most extreme outcomes of stellar evolution. They are the compressed remnants of once massive stars, transformed into objects of incredible density, speed, and energy. They bridge the gap between ordinary matter and the most extreme conditions in the universe, offering insight into the behavior of physics under conditions that cannot be recreated anywhere else. In the broader story of the universe, neutron stars are a reminder that even in death, stars continue to shape reality. They mark the boundary between order and collapse, between known physics and the unknown. Through their pulses of radiation and their violent collisions, they reveal hidden aspects of the cosmos and connect the life cycle of stars to the creation of elements and the structure of galaxies. As we continue to observe them, neutron stars and pulsars will remain essential guides in our exploration of the universe. They are not just remnants of stellar destruction, but active participants in the ongoing evolution of space, matter, and time. Supernova explosions are among the most powerful and dramatic events in the universe. They mark the violent end of a star's life, a final act of destruction that can briefly outshine entire galaxies and reshape the cosmic environment around them. Yet, despite their destructive nature, supernovae are also deeply creative forces. They are responsible for producing many of the elements that make up planets, atmospheres, oceans, and even living organisms. In a very real sense, the death of stars is also the origin of complexity in the universe. Without supernovae, the cosmos would remain a simple place, composed mostly of hydrogen and helium, without the rich diversity of matter that allows worlds and life to exist. A supernova begins with a star that has reached the end of its life cycle. Stars are powered by nuclear fusion in their cores, where lighter elements such as hydrogen are fused into heavier elements like helium, releasing energy that counteracts the force of gravity. This balance between outward pressure and inward collapse keeps a star stable for most of its existence. However, this balance is temporary. Over millions or billions of years, depending on the mass of the star, the fuel in the core begins to run out. Once fusion can no longer sustain the pressure needed to resist gravity, the star enters its final stages of evolution. For massive stars, the process of collapse is particularly dramatic. As nuclear fuel is exhausted in successive layers, the core begins to contract under its own weight. This contraction increases the temperature and pressure in the core, allowing heavier elements to form through fusion. The star essentially builds layered shells of fusion, each producing progressively heavier elements such as carbon, oxygen, neon, silicon, and finally iron. Iron represents a critical point in this process because it does not release energy when fused. Instead, it consumes energy. Once the core becomes dominated by iron, fusion can no longer provide outward pressure. At this stage, the star's fate is sealed. When the iron core grows beyond a certain limit, known as the Chandrasekhar limit in some cases, gravity overwhelms all resisting forces. The core collapses in a fraction of a second, shrinking from thousands of kilometers across to a sphere only a few tens of kilometers in diameter. During this collapse, protons and electrons are forced together to form neutrons, releasing an enormous number of neutrinos. These nearly massless particles carry away vast amounts of energy, briefly dominating the energy output of the collapsing star. As the core collapses, the outer layers of the star fall inward at tremendous speeds. However, the core suddenly becomes extremely dense and stiff due to neutron degeneracy pressure, causing the infalling material to rebound outward in a massive shockwave. This rebound, combined with energy from neutrinos, triggers the explosion that we observe as a supernova. The outer layers of the star are violently expelled into space at speeds of thousands of kilometers per second, carrying with them newly formed elements forged in the star's interior. The energy released in a supernova is staggering. In a matter of seconds, a single exploding star can release more energy than the sun will emit over its entire 10 billion year lifetime. For a short period, the supernova can outshine an entire galaxy, making it visible across vast cosmic distances. Ancient civilizations occasionally recorded these events in the night sky, often interpreting them as new stars appearing unexpectedly. Modern astronomy has revealed their true nature as catastrophic stellar deaths. There are different types of supernovae, each with distinct origins and characteristics. The most common type associated with massive stars is known as a core collapse supernova. This occurs when a massive star exhausts its nuclear fuel and its core collapses under gravity. Another important type is the thermonuclear supernova, which occurs in binary star systems involving white dwarfs. In these systems, a white dwarf can accumulate matter from a companion star until it reaches a critical mass, triggering a runaway nuclear reaction that completely destroys the star. Unlike core collapse supernovae, which leave behind neutron stars or black holes, thermonuclear supernovae often destroy their progenitor completely. Core collapse supernovae are particularly important because they are responsible for the formation of neutron stars and black holes. When the collapsing core is not massive enough to form a black hole, it stabilizes as a neutron star. If the core is sufficiently massive, the collapse continues beyond the neutron star stage, forming a black hole. In both cases, the outer layers of the star are expelled into space, enriching the surrounding environment with heavy elements. The material ejected by supernovae plays a crucial role in the chemical evolution of the universe. Inside the cores of massive stars, nuclear fusion creates elements up to iron. However, elements heavier than iron require even more energetic processes to form. Supernova explosions provide the necessary energy to create these heavier elements through rapid neutron capture processes. Elements such as gold, silver, uranium, and platinum are believed to be formed in these extreme environments. Without supernovae, these elements would not exist in the universe. The shock waves produced by supernovae also have a profound impact on their surrounding environment. As the explosion expands outward, it compresses nearby clouds of gas and dust. This compression can trigger the formation of new stars by causing regions of the interstellar medium to collapse under gravity. In this way, supernovae not only mark the end of one generation of stars, but also contribute to the birth of new ones. This cycle of stellar death and rebirth is a fundamental process in the evolution of galaxies. Supernova remnants, the expanding clouds of gas and debris left behind after the explosion, are some of the most visually striking structures in the universe. These remnants can persist for thousands of years, gradually dispersing their material into the surrounding space. They often exhibit complex filamentary structures shaped by magnetic fields and shock waves. Observations of supernova remnants provide valuable information about the composition of the original star and the dynamics of the explosion itself. One of the most famous supernova remnants is the Crab Nebula, which is the result of a supernova observed on Earth in the year 1054. Historical records from multiple civilizations describe a bright object in the sky, visible even during the day for several weeks. Today, the Crab Nebula is studied extensively in modern astronomy and contains a rapidly rotating neutron star at its center, known as a pulsar. This connection between historical observation and modern science highlights the long-term impact of supernova events. Supernovae also play a critical role in shaping galaxies. The energy released by these explosions can drive powerful shock waves through the interstellar medium, heating gas and regulating star formation. In some cases, repeated supernova explosions in a region can create large cavities known as superbubbles, which can extend for hundreds of light years. These structures influence the distribution of matter in galaxies and contribute to their overall evolution. In addition to their role in chemical enrichment and star formation, supernovae are also important for understanding the expansion of the universe. Type Ia supernovae, which occur in binary systems involving white dwarfs, have a very consistent intrinsic brightness. This makes them useful as standard candles for measuring cosmic distances. By comparing their observed brightness with their known intrinsic brightness, astronomers can determine how far away they are. This method has been instrumental in discovering that the expansion of the universe is accelerating, leading to the concept of dark energy. The study of supernovae also provides insight into the behavior of matter under extreme conditions. During the explosion, temperatures reach billions of degrees, and matter exists in states that cannot be reproduced on Earth. The physics of shock waves, neutrino interactions, and nuclear reactions all come together in a complex and dynamic environment. Understanding these processes requires advanced simulations and observations across multiple wavelengths, including visible light, X-rays, gamma rays, and neutrinos. One of the most important recent developments in supernova research is the detection of neutrinos from a supernova. In 1987, a supernova occurred in a nearby galaxy called the Large Magellanic Cloud. For the first time, detectors on Earth captured neutrinos emitted during the collapse of the star. These particles provided direct information about the core collapse process, confirming theoretical predictions about how supernovae work. This event marked the beginning of neutrino astronomy and opened a new window into studying the universe. Despite decades of study, many aspects of supernova explosions remain uncertain. The exact mechanism by which the shock wave successfully escapes the collapsing core is still not fully understood. Simulations suggest that neutrinos play a key role in reviving the stalled shock, but the details are complex and continue to be refined. Understanding this process is one of the major challenges in modern astrophysics. Supernovae also raise important questions about the fate of matter in the universe. When a star explodes, it disperses its material into space. But that material eventually becomes part of new stars, planets, and even living organisms. The atoms in our bodies, including carbon, oxygen, and iron, were once formed in the cores of ancient stars and later scattered by supernova explosions. In this way, supernovae are not just distant cosmic events, they are directly connected to our existence. As we observe more supernovae in distant galaxies, we gain a better understanding of how common these events are and how they influence the evolution of the universe. Modern telescopes allow us to detect supernovae at great distances, revealing explosions that occurred billions of years ago. By studying these distant events, we are effectively looking back in time, observing the history of the universe as it unfolded. Supernova explosions represent one of the most important processes in the cosmos. They mark the end of stellar life, but also the beginning of new cosmic cycles. They create the elements that make up planets and life, influence the structure of galaxies, and help us measure the expansion of the universe. They are both destructive and creative, violent and essential. In the grand story of the universe, supernovae are moments of transformation. They remind us that even in destruction there is creation, and even in death there is renewal. Through their immense energy and far-reaching effects, they connect the life cycles of stars to the broader evolution of the cosmos, shaping everything from the smallest atoms to the largest structures in existence. In the vast structure of the universe, there exists a force that cannot be seen, cannot be directly measured with light, and does not interact with ordinary matter in any way we currently understand. Yet its presence is undeniable, shaping galaxies, bending the paths of stars, and holding the cosmic web together. This mysterious substance is known as dark matter. It does not emit radiation, it does not absorb or reflect light, and it does not appear in any form of electromagnetic observation. Still, without it, the universe as we know it would fall apart. Galaxies would not rotate the way they do, clusters of galaxies would not hold together, and the large-scale structure of the cosmos would look completely different. The story of dark matter begins with a simple but powerful observation. When astronomers studied the rotation of galaxies, they expected to find that stars closer to the center of a galaxy would orbit faster, while stars farther away would move more slowly, similar to how planets in the solar system behave. This expectation comes from the fact that most of the visible mass in a system is concentrated near the center. However, when measurements were made, the results were surprising. Stars at the outer edges of galaxies were moving just as fast as those near the center. This meant that there had to be more mass in galaxies than what could be seen. This discrepancy led to the conclusion that galaxies must contain a large amount of unseen matter. This invisible mass does not interact with light, which is why it cannot be observed directly. It only reveals itself through its gravitational effects. This unknown component was named dark matter. Over time, additional evidence for its existence began to accumulate from different areas of astronomy and cosmology. One of the most important pieces of evidence comes from the study of galaxy clusters. When scientists measured the motion of galaxies within clusters, they found that the visible matter alone was not enough to keep the clusters gravitationally bound. Without additional mass, the galaxies would move too fast and fly apart. The presence of dark matter provides the extra gravitational glue needed to hold these structures together. Another key line of evidence comes from gravitational lensing. According to Einstein's theory of general relativity, massive objects bend the fabric of space-time, causing light to follow curved paths. When light from distant galaxies passes through regions containing large amounts of mass, such as galaxy clusters, it becomes distorted. By studying these distortions, astronomers can map the distribution of mass in the universe. These maps consistently show that there is far more mass present than what can be accounted for by visible matter alone. The excess mass is attributed to dark matter. The cosmic microwave background radiation also provides strong evidence for dark matter. This faint glow, which is the afterglow of the early universe, contains tiny fluctuations in temperature and density. These fluctuations reflect the distribution of matter in the early cosmos. When scientists analyze these patterns, they find that the formation of structures, such as galaxies and clusters, requires the presence of a large amount of non-visible matter. Without dark matter, the observed structure of the universe could not have formed in the way we see it today. Despite its importance, the true nature of dark matter remains one of the greatest mysteries in modern science. It does not interact with electromagnetic radiation, which means it cannot be seen with telescopes. It does not appear to be made of atoms or any known particles in the standard model of physics. This has led scientists to propose that dark matter is made of entirely new types of particles that have not yet been detected in laboratories. One of the leading candidates for dark matter particles is known as weakly interacting massive particles, or WIMPs. These hypothetical particles would have mass, but would interact only very weakly with ordinary matter, making them extremely difficult to detect. Another candidate is the axion, a very light particle that could exist in large quantities throughout the universe. There are also theories that suggest dark matter could be composed of primordial black holes formed in the early universe, although this idea remains controversial. Despite many efforts, no direct detection of dark matter particles has yet been confirmed. Experiments deep underground, in space, and in particle accelerators are all searching for evidence of these elusive particles. Scientists are trying to detect rare interactions between dark matter and ordinary matter, but so far the results remain inconclusive. This has led some researchers to consider alternative explanations, including the possibility that our understanding of gravity itself may need to be modified on large scales. One such alternative theory is known as modified Newtonian dynamics, or MOND. This idea suggests that the laws of gravity behave differently at very low accelerations, which could explain the observed rotation of galaxies without requiring dark matter. However, while MOND can explain some galactic behavior, it struggles to account for observations on larger scales, such as galaxy clusters and the cosmic microwave background. As a result, dark matter remains the most widely accepted explanation. Even though we cannot see dark matter, we can map its distribution across the universe using its gravitational effects. These maps reveal that dark matter forms a vast cosmic network known as the cosmic web. This structure consists of long filaments of dark matter that stretch across the universe, connecting clusters of galaxies like a vast invisible scaffolding. Galaxies form and evolve along these filaments, drawn together by gravity into dense nodes where clusters and superclusters emerge. Between these filaments are enormous voids, regions with very little matter, where galaxies are sparse. The cosmic web is one of the largest known structures in the universe, and dark matter is its backbone. Without it, the distribution of galaxies would be much more random and less organized. The formation of galaxies themselves is deeply influenced by dark matter. In the early universe, small fluctuations in the density of dark matter provided gravitational wells into which ordinary matter could fall. As gas accumulated in these regions, it cooled and formed stars and galaxies. Without dark matter, the process of galaxy formation would have been far less efficient, and the universe might not have developed the complex structure we observe today. Dark matter also plays a crucial role in galaxy stability. In spiral galaxies like the Milky Way, stars rotate around the galactic center in well-defined patterns. Without additional mass provided by dark matter, The outer stars would not have enough gravitational pull to remain in stable orbits. Instead, they would drift away into space. The presence of dark matter halos surrounding galaxies provides the necessary gravitational support to keep these structures intact. These dark matter halos extend far beyond the visible edges of galaxies. They are massive, spherical regions that contain most of the mass of a galaxy, even though they cannot be seen directly. The visible stars and gas that we observe make up only a small fraction of the total mass. The rest is hidden in these extended halos which dominate the gravitational structure of galaxies. The influence of dark matter is not limited to galaxies. It also affects the expansion and evolution of the universe as a whole. In the early universe, dark matter helped seed the formation of large-scale structures by amplifying small density fluctuations. Over time, these fluctuations grew under the influence of gravity, leading to the formation of galaxies, clusters, and the cosmic web. Without dark matter, the universe would have remained much smoother and less structured. One of the most important goals in modern cosmology is to understand the relationship between dark matter and dark energy. Together, these two mysterious components make up most of the total energy content of the universe. Dark matter accounts for about 27%, while dark energy makes up about 68%. Ordinary matter, the kind that makes up stars, planets, and living beings, represents only a small fraction of the total. This means that the vast majority of the universe is composed of substances that we do not fully understand. The study of dark matter is closely linked to particle physics, astrophysics, and cosmology. Scientists are using a wide range of experiments to search for evidence of dark matter particles. These include underground detectors designed to capture rare interactions, space-based telescopes that look for indirect signals, such as gamma rays, and high-energy particle accelerators that attempt to create dark matter particles in controlled environments. Each of these approaches provides different pieces of the puzzle, but the full picture remains incomplete. In addition to experimental searches, computer simulations play a crucial role in understanding dark matter. By modeling the evolution of the universe with dark matter included, scientists can reproduce the large-scale structure observed in galaxy surveys. These simulations show how dark matter forms a cosmic web and guides the formation of galaxies over billions of years. The success of these models provides strong indirect support for the existence of dark matter. Despite its invisible nature, dark matter is one of the most important components of the universe. It shapes the structure of galaxies, influences the formation of cosmic structures, and holds the universe together on the largest scales. Without it, the universe would be dramatically different, possibly lacking the complexity necessary for stars, planets, and life to exist. Yet the true identity of dark matter remains unknown. It is one of the deepest mysteries in science, representing a gap in our understanding of the fundamental nature of reality. Solving this mystery could lead to a major breakthrough in physics, revealing new particles, new forces, or even new dimensions of space. In the ongoing exploration of the cosmos, dark matter stands as a silent but powerful presence. It cannot be seen, but its influence is everywhere. It is the invisible architecture of the universe, shaping everything from the smallest galaxies to the largest cosmic structures. As we continue to study it, we move closer to understanding the hidden side of the universe and the forces that govern its evolution. In the modern understanding of the universe, one of the most surprising discoveries is that the cosmos is not only expanding, but the rate of that expansion is increasing over time. This means that galaxies are not just moving away from each other due to the aftermath of the Big Bang, but they are accelerating apart as space itself stretches faster and faster. The force or phenomenon responsible for this acceleration is known as dark energy. It is one of the most mysterious components of the universe, and unlike anything else we have encountered in physics. It does not clump together like matter, it does not form structures like galaxies, and it does not appear to interact with light or particles in any direct way. Yet it dominates the large-scale behavior of the universe. The discovery of dark energy came as a shock to the scientific community. For most of the 20th century, cosmologists assumed that the expansion of the universe, which began with the Big Bang, would gradually slow down over time due to the gravitational pull of matter. Gravity is attractive, so it was expected that all the matter in the universe would be pulling on all other matter, slowing the expansion and possibly even leading to a future collapse in a scenario sometimes called the Big Crunch. The ultimate fate of the universe seemed to depend on how much matter it contained. If there was enough matter, gravity would eventually stop the expansion and reverse it. If there was not enough, the universe would expand forever, but at a slowing rate. However, in the late 1990s, two independent groups of astronomers studying distant exploding stars called Type Ia supernovae made a groundbreaking discovery. These supernovae are extremely useful in cosmology because they have a consistent intrinsic brightness, allowing scientists to use them as standard candles to measure cosmic distances. By comparing how bright they appear from Earth with how bright they actually are, researchers can determine how far away they are. What the astronomers found was unexpected. Distant supernovae were dimmer than they should have been if the expansion of the universe was slowing down. This meant that the expansion was not decelerating as expected, but accelerating. This discovery led to the conclusion that some unknown form of energy must be driving the acceleration. This energy was named dark energy. Unlike dark matter, which exerts gravitational attraction and helps hold galaxies together, dark energy appears to act in the opposite way. It pushes space itself apart on the largest scales, overcoming the attractive force of gravity between galaxies. To understand dark energy, it is important to understand the nature of space itself. In general relativity, space and time are not fixed backgrounds. They are dynamic entities that can expand, contract, and curve in response to matter and energy. The expansion of the universe is not galaxies moving through space away from a central point, but rather space itself stretching, carrying galaxies along with it. Dark energy influences this stretching, causing it to accelerate over time. One of the simplest explanations for dark energy comes from the concept of the cosmological constant. This idea was originally introduced by Albert Einstein in his equations of general relativity. Einstein initially added the cosmological constant to allow for a static universe which was the prevailing belief at the time. He later abandoned the idea after the discovery that the universe is expanding. However, the cosmological constant can also be interpreted as a property of space itself, representing a constant energy density that fills all of space uniformly. If this energy exists, it would cause space to expand at an accelerating rate. The cosmological constant is currently one of the leading explanations for dark energy. In this model, dark energy is not a dynamic force that changes over time, but a constant property of space. As the universe expands, more space is created, and therefore more dark energy exists, maintaining a constant density. This leads to continuous acceleration of the expansion. However, the true nature of dark energy may be more complex. Some theories suggest that it could be related to a dynamic field that evolves over time, similar to the inflaton field proposed in cosmic inflation. In these models, dark energy could change strength as the universe evolves, potentially leading to different future outcomes for the cosmos. These models are often referred to as quintessence theories. Despite many possibilities, dark energy remains one of the least understood aspects of physics. Unlike dark matter, which has at least some indirect evidence through gravitational effects on structures, dark energy is only observed through its influence on the expansion of the universe. It does not clump together, it does not emit signals, and it does not interact with matter in any known way except through gravity on the largest scales. Measurements from the cosmic microwave background radiation provide additional evidence for dark energy. By studying the patterns of temperature fluctuations in this ancient light, scientists can determine the overall geometry and composition of the universe. These measurements show that about 68% of the total energy content of the universe is in the form of dark energy, while dark matter makes up about 27% and ordinary matter only about 5%. This means that the vast majority of the universe is made up of substances that we do not directly understand. The presence of dark energy has profound implications for the future of the universe. If the current rate of acceleration continues, galaxies outside our local group will eventually move so far away that their light will no longer reach us. Over billions of years, the observable universe will shrink from our perspective as distant galaxies disappear beyond the cosmic horizon. Eventually, only galaxies gravitationally bound to our local group will remain visible. In an even more extreme scenario, the acceleration could increase over time, leading to a situation known as the Big Rip. In this hypothetical outcome, dark energy becomes so strong that it eventually overcomes all other forces, including the gravitational forces holding galaxies, stars, planets, and even atoms together. In this scenario, the universe would be torn apart at every scale. However, current observations suggest that this scenario is less likely, although it cannot be completely ruled out. Another possibility is that dark energy is truly constant, in which case the universe will continue expanding forever at an accelerating rate, gradually becoming colder, darker, and more empty. In this scenario, galaxies outside local gravitationally bound systems would drift apart, stars would eventually burn out, and the universe would approach a state of maximum entropy known as the heat death of the universe. In this final state, all energy would be evenly distributed and no thermodynamic processes could occur. The discovery of dark energy has also raised deep questions about the nature of space, time, and vacuum energy. In quantum field theory, even empty space is not truly empty. It is filled with fluctuations of energy at the smallest scales, where particles and antiparticles constantly appear and disappear. Some theories suggest that dark energy may be related to this vacuum energy, although calculations based on quantum physics predict a value that is vastly larger than what is observed. This discrepancy between theory and observation is one of the greatest unsolved problems in physics. Understanding dark energy may require a new framework that unifies quantum mechanics and general relativity. Current theories work extremely well in their respective domains, but they are incompatible when combined under extreme conditions, such as those involving dark energy or black holes. A theory of quantum gravity could potentially explain the true nature of dark energy and reveal why the universe behaves the way it does on the largest scales. Observational astronomy continues to play a key role in studying dark energy. Large surveys of galaxies map the distribution of matter across the universe, allowing scientists to measure how the expansion rate has changed over time. These surveys include measurements of baryon acoustic oscillations, which are subtle patterns in the distribution of galaxies that act as a cosmic ruler for measuring distances across billions of light years. By combining these observations with data from supernovae and the cosmic microwave background, scientists are gradually refining our understanding of dark energy. Despite these advances, dark energy remains deeply mysterious. It does not fit easily into our current understanding of physics, and it challenges our assumptions about the nature of the universe. It is not just a new type of matter or force. It may represent a fundamental property of space itself, or even something more profound that we have not yet conceptualized. The existence of dark energy also changes how we think about the universe as a whole. Instead of a static or slowly evolving system, the universe is dynamic and accelerating, driven by a force that we cannot yet explain. This realization has transformed cosmology from a study of structure and evolution into a deeper exploration of fundamental reality. As we continue to observe distant galaxies and measure the expansion of the universe with increasing precision, we move closer to understanding dark energy. Each new observation helps refine our models and narrow down the possibilities. Yet, the full picture remains elusive. The universe is expanding, accelerating, and evolving in ways that suggest there are still fundamental aspects of reality waiting to be discovered. Dark energy stands as one of the greatest mysteries in modern science. It governs the fate of the universe, shapes the structure of space on the largest scales, and defines the long-term future of everything that exists. Although invisible and unknown in nature, its effects are written across the cosmos. In studying dark energy, we are not just learning about a strange cosmic force. We are confronting the ultimate limits of our understanding of space, time, and existence itself. Among the most intriguing ideas in modern theoretical physics are wormholes, hypothetical structures that could connect distant regions of space and time through tunnels in the fabric of the universe. These are not physical tunnels in the conventional sense, but rather solutions to the equations of general relativity that suggest space-time itself can bend and fold in such a way that two far-apart locations might be linked by a shortcut. In simple terms, a wormhole is a bridge through space-time, potentially allowing travel between distant parts of the universe in a way that would be impossible through normal space. The concept of wormholes emerges directly from Einstein's theory of general relativity. According to this theory, gravity is not a force in the traditional sense, but a curvature of space-time caused by mass and energy. Massive objects like stars and black holes distort the geometry of space-time around them. Under certain mathematical conditions, these distortions can create structures that resemble tunnels connecting two separate points. The most famous theoretical example is the Einstein-Rosen bridge, proposed in 1935 by Albert Einstein and Nathan Rosen. This was one of the earliest attempts to describe what we now call a wormhole. In the simplest interpretation, a wormhole consists of two mouths connected by a throat. The mouths are regions in space-time that could be separated by vast distances, even on opposite sides of the universe. The throat is the connecting region that links them. If such a structure were stable and traversable, it could allow an object to enter one mouth and emerge from the other almost instantaneously, effectively bypassing the normal distance between the 2 points. However, the original Einstein-Rosen bridge is not stable. It collapses too quickly for anything to pass through. In this form, it is not a usable wormhole, but rather a mathematical curiosity that appears in the equations of general relativity. For a wormhole to be traversable, it would require some form of exotic matter or energy that could stabilize the throat and prevent it from collapsing. This exotic matter would need to have unusual properties, including negative energy density, which is not something we typically observe in normal matter. The idea of negative energy is deeply connected to quantum physics. In certain quantum field effects, such as the Casimir effect, regions of space can exhibit negative energy densities relative to the vacuum. These effects are extremely small and occur only under very specific conditions, but they suggest that the laws of physics might allow for the existence of exotic states of energy that could, in theory, stabilize a wormhole. However, whether this could be scaled up to macroscopic structures remains unknown. Wormholes are not just shortcuts through space, they are also closely related to the structure of space-time itself. In general relativity, space and time are woven together into a four-dimensional fabric. Massive objects curve this fabric, and wormholes represent extreme distortions where the fabric folds back on itself. In this sense, a wormhole is not a hole in space, but rather a tunnel through the geometry of space-time. One of the most fascinating implications of wormholes is their connection to time travel. Because space and time are linked, a wormhole that connects two different points in space could also connect two different points in time. If one mouth of a wormhole were moved at high speed relative to the other, time dilation effects predicted by relativity would cause time to pass differently at each end. This could potentially create a situation where one mouth is in the future relative to the other. In such a scenario, entering the wormhole could allow travel not only across space, but across time. This possibility leads to deep paradoxes and questions about causality. If time travel were possible through wormholes, it could allow for situations where cause and effect are reversed, or where events influence their own origins. For example, an object could be sent through a wormhole into the past, potentially altering events in a way that creates contradictions. These paradoxes challenge our understanding of logic and the structure of reality. To address these issues, some physicists have proposed that nature may prevent the formation of time paradoxes through a principle known as chronology protection. This idea suggests that the laws of physics may prevent macroscopic time travel from occurring, even if the equations of general relativity allow it mathematically. In this view, wormholes might exist only in forms that cannot be used for time travel, or might be inherently unstable when used in such a way. Despite these challenges, wormholes remain an active area of theoretical research. They appear naturally in many solutions to Einstein's equations, especially in the context of black holes. In fact, some models suggest that black holes themselves might be connected to other regions of space-time through wormhole-like structures. In these models, a black hole could act as one mouth of a wormhole, with the other mouth potentially located elsewhere in the universe or even in another universe entirely. However, there is currently no observational evidence for such connections. The idea of traversable wormholes was further developed in the late 20th century by physicists such as Kip Thorne and Michael Morris. They explored the conditions under which a stable wormhole might exist and what type of exotic matter would be required to keep it open. Their work showed that while wormholes are not forbidden by the laws of physics, they would require conditions that are far beyond anything we currently know how to create or observe. One of the key challenges in wormhole physics is stability. Even if a wormhole could be created, it would likely be extremely unstable. Small perturbations in energy or matter could cause it to collapse instantly. The gravitational forces near the throat of a wormhole would be extreme, and quantum effects might play a significant role in its behavior. These factors make it difficult to determine whether wormholes could exist in a stable, usable form in the real universe. Another major question is how wormholes might form naturally. While they are often discussed in the context of theoretical physics, it is unclear whether natural processes could produce them. Some speculative ideas suggest that microscopic wormholes might have formed in the early universe due to quantum fluctuations in space-time. These primordial wormholes, if they exist, would likely be extremely small and unstable, possibly existing only at the quantum level. However, if they could be stabilized or enlarged, they might have profound implications for cosmology and physics. Wormholes also appear in the context of quantum gravity, a theoretical framework that attempts to unify general relativity with quantum mechanics. In some approaches, space-time itself is not smooth and continuous, but made up of discrete or fluctuating structures at the smallest scales. In such a picture, wormholes could be common at the quantum level, constantly appearing and disappearing in a foamy structure known as space-time foam. This idea suggests that the fabric of the universe may be far more dynamic and complex than previously thought. In addition to their role in theoretical physics, Wormholes have also become a popular concept in science fiction. They are often used as a narrative device to enable faster-than-light travel between distant stars or galaxies. While this use is speculative, it is based on real mathematical solutions in general relativity. However, science fiction often simplifies or overlooks the enormous physical challenges involved in stabilizing and traversing a wormhole. From an observational standpoint, there is currently no evidence that wormholes exist in the universe. However, scientists have proposed ways in which they might be detected indirectly. For example, a wormhole could potentially produce unusual gravitational lensing effects, where light from distant objects is distorted in ways that cannot be explained by ordinary matter. It might also produce unique gravitational wave signatures if it interacts with other massive objects. These possibilities are highly speculative, but they provide potential avenues for future research. If wormholes do exist and are traversable, they would fundamentally change our understanding of space and time. They would allow for shortcuts across the universe, making interstellar travel vastly more efficient. Distances that currently take millions or billions of years for light to cross could potentially be traversed instantly. This would reshape not only physics, but also the possibilities for exploration and communication across the cosmos. However, even if wormholes exist, the energy requirements to create or stabilize them may be beyond anything achievable by any known civilization. The amount of exotic matter or negative energy needed is unknown, but estimates suggest it could be enormous. This places wormholes firmly in the realm of theoretical possibility rather than practical engineering, at least with our current understanding of physics. Wormholes also raise profound philosophical questions about the nature of reality. If space-time can be folded and connected in such unusual ways, then the universe may be far more interconnected than it appears. The idea that distant regions of the cosmos could be linked through hidden tunnels suggests that our perception of separation and distance may be incomplete. It challenges the intuitive idea that space is a simple, continuous expanse, and instead suggests a complex and dynamic structure beneath the surface. In the broader context of cosmology, wormholes represent one of the many ways in which the universe defies simple understanding. Alongside black holes, dark matter, and dark energy, they highlight the limits of current physics and point toward a deeper theory of reality that has yet to be discovered. Whether or not wormholes exist in a physical sense, they play an important role in pushing the boundaries of theoretical exploration. As our understanding of quantum mechanics, gravity, and cosmology continues to evolve, wormholes remain a fascinating possibility. They sit at the intersection of known physics and speculative theory, representing both the power and the limitations of our current scientific framework. They remind us that the universe may contain structures and phenomena far more exotic than anything we have yet observed. In the end, wormholes are not just about travel or shortcuts. They are about the structure of reality itself. They force us to consider whether space and time are fixed and rigid or flexible and interconnected in ways we do not yet fully understand. Whether they exist in nature or remain purely theoretical, wormholes continue to inspire scientific inquiry and expand our imagination about what the universe might be capable of. In the vast darkness between stars, far from the familiar glow of any sun, there exist objects that wander through space with no home, no orbit, and no parent star to guide them. These are known as rogue planets, also called interstellar planets or orphan worlds. They are planetary bodies that drift freely through the galaxy, unbound by gravity to any star system. Unlike the planets in our solar system, which orbit the Sun in stable paths, rogue planets travel through interstellar space alone, carried only by the gravitational structure of the galaxy itself. Their existence challenges our traditional understanding of planetary systems and reveals a universe that is far more dynamic and chaotic than once imagined. The origin of rogue planets is deeply tied to the formation and evolution of planetary systems. Planets are born in protoplanetary disks, vast rotating clouds of gas and dust that surround young stars. Within these disks, particles collide and gradually clump together, forming larger and larger bodies over time. Eventually, these bodies become planets, moons, and other celestial objects. In a stable system, these planets settle into long-term orbits around their parent star. However, the early stages of planetary formation are often violent and unstable. Gravitational interactions between forming planets can lead to dramatic changes in their orbits. In some cases, a young planet may be gravitationally ejected from its system entirely. This can happen when multiple large planets interact closely, exchanging energy and momentum in chaotic ways. A close encounter between two massive planets can result in one being flung outward with enough velocity to escape the gravitational pull of its star. Once this happens, the planet is no longer bound to any solar system and begins its journey through interstellar space as a rogue planet. This process is thought to be one of the most common ways rogue planets are created. Another possible origin for rogue planets is the early instability of planetary systems themselves. During the formation of a star system, not all planets settle into stable orbits immediately. Some may form in regions where gravitational forces are still shifting, leading to unstable trajectories that eventually result in ejection. In densely packed star clusters, gravitational interactions between neighboring stars can also disturb planetary systems, increasing the likelihood of planets being expelled into interstellar space. There is also the possibility that some rogue planets form directly in space without ever being part of a star system. These objects, sometimes referred to as sub-brown dwarfs or failed stars, may form from the collapse of gas clouds that are too small to ignite nuclear fusion. While they are similar to planets in size, their origin is more like that of stars, formed through gravitational collapse rather than accretion in a disk. Whether these objects should be classified as planets or something else entirely remains a topic of debate. Detecting rogue planets is extremely difficult because they do not emit their own light and are not illuminated by a nearby star. They are cold, dark, and isolated, making them nearly invisible against the backdrop of space. However, astronomers have developed indirect methods to detect them. One of the most effective techniques is gravitational microlensing. This method relies on the fact that massive objects bend light as it passes near them. When a rogue planet passes in front of a distant star, its gravity briefly magnifies the light of that star, creating a detectable signal. By carefully analyzing these events, scientists can infer the presence of otherwise invisible planets. Observations using microlensing have suggested that rogue planets may be far more common than previously thought. Some estimates indicate that there could be billions of rogue planets in our galaxy alone, possibly even more than the number of stars. This means that interstellar space may be filled with countless wandering worlds, silently drifting through the Milky Way. However, these estimates are still uncertain, and the true population of rogue planets remains one of the open questions in astronomy. The conditions on rogue planets are likely to be extremely harsh. Without a nearby star, they receive no sunlight and exist in near total darkness. Their surface temperatures would be extremely low, often just a few degrees above absolute zero, depending on internal heat sources. Any atmosphere they might have would likely freeze or collapse unless sustained by internal geothermal activity. Despite these extreme conditions, some rogue planets may still retain internal heat generated by radioactive decay or residual energy from their formation. This internal heat could potentially create subsurface environments where liquid water might exist beneath a thick layer of ice. This possibility has led scientists to speculate about the potential habitability of rogue planets. While they are not in the traditional habitable zones of stars, internal heat sources could create environments similar to the subsurface oceans believed to exist on moons such as Europa or Enceladus in our own solar system. If liquid water exists beneath the surface of a rogue planet, it is theoretically possible that microbial life could survive in such environments, protected from the harsh conditions of interstellar space by thick layers of ice and rock. The idea of life on rogue planets is highly speculative, but it expands the traditional concept of habitability beyond the presence of a star. Instead of relying on sunlight, life in these environments would depend on geothermal energy or chemical processes. This shifts the focus from surface conditions to internal environments, opening new possibilities for where life might exist in the universe. Rogue planets also raise interesting questions about the dynamics of galaxies. As these objects drift through interstellar space, they interact weakly with the gravitational field of the galaxy. Over long periods of time, they may pass through different regions, occasionally encountering star systems, or even being captured by them. In some cases, a rogue planet could be captured into orbit around a star, becoming part of a new planetary system. This process of capture and ejection suggests that planetary systems are not static, but constantly exchanging material over billions of years. The motion of rogue planets through the galaxy is governed primarily by gravity. They do not move in straight lines, but follow complex trajectories influenced by the combined gravitational pull of stars, gas clouds, and dark matter. Their paths can be extremely long and slow, taking millions or even billions of years to traverse significant distances. Over time, they become part of the larger structure of the galaxy, embedded within the gravitational framework shaped by dark matter and stellar distributions. Some rogue planets may also carry with them remnants of their original systems. Moons, rings, or even atmospheres could remain intact after ejection, at least for a period of time. These systems would be isolated and slowly evolving, cut off from external energy sources. The long-term stability of such systems is uncertain, but they represent fascinating examples of planetary survival under extreme conditions. The discovery of rogue planets has significant implications for our understanding of planetary formation. It suggests that planet formation is not always a neat and orderly process, but can be chaotic and destructive. Many planets may never remain in stable orbits around a star, and instead spend most of their existence wandering through interstellar space. This challenges the traditional view that planets are primarily defined by their relationship to a star. Rogue planets also provide insight into the gravitational dynamics of star systems. By studying how and why planets are ejected, scientists can better understand the processes that shape planetary architectures. This includes the role of orbital resonance, gravitational scattering, and interactions between multiple planets. These processes are not only important for understanding rogue planets, but also for explaining the diversity of planetary systems observed throughout the galaxy. In addition to their scientific importance, rogue planets also capture the imagination because of their isolation. They are worlds without suns, traveling through the darkness of space with no fixed destination. In a sense, they represent a different kind of cosmic existence, one that is not defined by stability or permanence, but by motion and change. They are reminders that the universe is not composed only of well-ordered systems, but also of objects that exist in constant transition. The study of rogue planets is still in its early stages. As observational techniques improve, especially in the field of gravitational microlensing and infrared astronomy, more of these hidden worlds are likely to be discovered. Future telescopes may even be able to directly detect the faint heat signatures of nearby rogue planets, providing more detailed information about their composition and structure. Some theoretical models suggest that rogue planets could even play a role in the long-term evolution of galaxies. As they move through space, they may interact with gas clouds, triggering local gravitational effects that contribute to star formation. Although their individual mass is small compared to stars, their sheer number could make them collectively significant in certain regions of the galaxy. Rogue planets also challenge our perception of what it means for a planet to exist. Traditionally, a planet is defined by its orbit around a star. However, rogue planets exist independently of this definition. They force us to reconsider whether a planet should be defined by its physical properties alone or by its relationship to a star. This question highlights the evolving nature of scientific classification as new discoveries reshape our understanding of the universe. In the grand structure of the cosmos, rogue planets are silent travelers. They do not shine, they do not orbit, and they do not announce their presence through light or radiation. Yet they are likely numerous, filling the space between stars with hidden worlds. Each one carries the history of its origin, a story of formation, instability, and ejection written into its frozen surface and internal structure. As we continue to explore the galaxy, rogue planets remind us that not all worlds are anchored to stars. Some drift endlessly through the dark, shaped only by gravity and time. They expand our understanding of planetary systems and reveal a universe that is far more diverse and dynamic than once believed. In their silent journeys across interstellar space, rogue planets embody the vastness and unpredictability of the cosmos itself. In the vast structure of the universe, one of the most powerful and visually dramatic processes is the interaction between galaxies. These immense systems, each containing billions or even trillions of stars, are not isolated islands in space. They are part of a constantly evolving cosmic environment where gravity slowly pulls them together, reshapes them, and in many cases merges them into entirely new structures. Galactic collisions and mergers are among the most important events in cosmic evolution, driving the growth of galaxies, triggering bursts of star formation, and reshaping the large-scale structure of the universe over billions of years. To understand galaxy collisions, it is important to first understand what galaxies are. A galaxy is a massive system held together by gravity, consisting of stars, stellar remnants, gas, dust, and a large amount of dark matter. Galaxies come in many shapes and sizes, including spiral galaxies like the Milky Way, elliptical galaxies that are more rounded and featureless, and irregular galaxies that lack a defined structure. Despite their enormous size, galaxies are not static. They move through space, influenced by the gravitational pull of nearby galaxies, galaxy clusters, and the underlying cosmic web shaped by dark matter. Although the distances between individual stars within a galaxy are vast, the distances between galaxies themselves are even greater. Because of this, direct collisions between stars during galaxy mergers are extremely rare. Instead, galaxies pass through each other, and their structures are gradually distorted by gravitational forces. Over time, these interactions can lead to dramatic changes in their shapes and internal dynamics. The process of a galaxy collision begins long before the actual merging of stars or structures. As two galaxies approach each other, their mutual gravitational attraction begins to distort their shapes. Spiral arms may become stretched and twisted, tidal tails of stars and gas can be pulled outward into space, and regions of dense star formation may be triggered by the compression of gas clouds. These early stages of interaction can last for hundreds of millions or even billions of years. One of the most striking features of interacting galaxies is the formation of tidal tails. These are long, stream-like structures made of stars and interstellar material that are pulled out from the main bodies of galaxies due to gravitational forces. Tidal tails can extend for hundreds of thousands of light-years, creating beautiful and complex patterns in space. They are a direct result of the uneven gravitational forces acting on different parts of the galaxies during close encounters. As the interaction continues, the galaxies begin to lose their distinct shapes. Their stellar orbits are disrupted, and the ordered motion seen in spiral galaxies becomes more chaotic. Gas clouds within the galaxies are compressed, leading to bursts of star formation known as starbursts. These starbursts can produce enormous numbers of new stars in a relatively short period of time, dramatically increasing the brightness of the interacting galaxies. Eventually, the galaxies begin to merge into a single system. The stars from both galaxies settle into new orbits determined by the combined gravitational potential. The resulting galaxy may take on a completely different shape from its progenitors. For example, when two spiral galaxies merge, the result is often an elliptical galaxy with a more random distribution of stars. This transformation shows that galaxy morphology is not fixed, but evolves through interactions over cosmic time. One of the most important examples of galactic interaction is the future collision between the Milky Way and the Andromeda galaxy. Andromeda, the nearest large galaxy to our own, is currently moving toward the Milky Way at a speed of about 110 kilometers per second. In approximately 4 to 5 billion years, the two galaxies are expected to collide and eventually merge. Although this sounds catastrophic, the vast distances between stars mean that direct collisions between individual stars are extremely unlikely. Instead, the solar system will likely be carried along in the new merged structure without being destroyed. During this merger, the night sky from Earth would be transformed dramatically. Over time, the Andromeda galaxy would grow larger and brighter in the sky until it dominates the view. As the galaxies begin to interact, the structure of the Milky Way would become distorted, with spiral arms stretching and warping. New bursts of star formation would light up regions of space with intense brightness. Eventually, the two galaxies would merge into a single, larger, elliptical galaxy, sometimes referred to as Milkomeda or Milkdromeda. The dynamics of galaxy mergers are governed not only by visible matter, but also by dark matter. Each galaxy is surrounded by a vast halo of dark matter that extends far beyond its visible structure. When galaxies interact, their dark matter halos also interact, merging and reshaping the gravitational environment. This dark matter plays a crucial role in determining how galaxies merge and what the final structure will be. In addition to mergers between large galaxies, there are also interactions involving smaller satellite galaxies. Many large galaxies, including the Milky Way, are surrounded by smaller companion galaxies that orbit them. Over time, these smaller galaxies can be pulled in by gravitational forces and absorbed into the larger galaxy. This process, known as galactic cannibalism, contributes to the growth of large galaxies over billions of years. Galaxy collisions also have a profound effect on black holes. Most large galaxies contain supermassive black holes at their centers. When two galaxies merge, their central black holes eventually come together as well. This process can lead to the formation of binary black hole systems, which orbit each other and gradually lose energy through the emission of gravitational waves. Eventually, these black holes merge into a single, more massive black hole, releasing enormous amounts of energy in the form of gravitational radiation. These black hole mergers are among the most energetic events in the universe. The gravitational waves they produce ripple through space-time, carrying information about the masses and spins of the merging objects. The detection of these waves has opened a new field of astronomy, known as gravitational wave astronomy, allowing scientists to observe cosmic events that were previously invisible. Galaxy mergers also influence the rate of star formation in the universe. When galaxies collide, the compression of gas clouds leads to the rapid formation of new stars. These starburst regions can produce massive, short-lived stars that eventually end their lives in supernova explosions. This cycle of star formation and destruction plays a key role in enriching the interstellar medium with heavy elements and shaping the chemical evolution of galaxies. However, not all galaxy interactions lead to increased star formation. In some cases, the energy released by active galactic nuclei powered by accreting supermassive black holes can heat surrounding gas and prevent it from collapsing into new stars. This process, known as feedback, can suppress star formation and regulate the growth of galaxies over time. On the largest scales, galaxy collisions contribute to the formation of galaxy clusters and superclusters. Galaxies are not evenly distributed throughout the universe, but are arranged in a vast cosmic web of filaments and nodes. Where these filaments intersect, galaxy clusters form, containing hundreds or thousands of galaxies bound together by gravity. Collisions and mergers within these clusters are common and play a major role in shaping their structure. Over billions of years, galaxy collisions lead to the gradual evolution of the universe from a more clumpy and irregular state to a more organized, large-scale structure. Smaller galaxies merge to form larger ones, and clusters merge to form superclusters. This hierarchical process of structure formation is driven by gravity and shaped by the distribution of dark matter. Despite the violence of these events, galaxy collisions are not sudden or chaotic in the way that everyday collisions might be imagined. They are slow, graceful processes that unfold over enormous timescales. The vast distances between stars mean that the universe operates on scales that are difficult for human intuition to grasp. What appears as a collision is actually a long-term gravitational dance between massive systems. Computer simulations play a crucial role in understanding galaxy mergers. By modeling the gravitational interactions between billions of particles representing stars, gas, and dark matter, scientists can recreate the process of galaxy collisions in great detail. These simulations show how tidal forces shape galaxies, how gas clouds collapse to form new stars, and how dark matter halos merge over time. They provide a window into processes that unfold over billions of years and cannot be observed directly. Observational astronomy also provides direct evidence of galaxy collisions in various stages of evolution. Telescopes have captured images of interacting galaxies, many of which show distorted shapes, tidal tails, and regions of intense star formation. These observations confirm that galaxy mergers are not rare events, but a fundamental part of cosmic evolution. On the largest scale, galaxy collisions are part of the ongoing evolution of the universe itself. They reflect the dynamic nature of gravity and the continuous reshaping of cosmic structures. Over time, the universe transitions from a state of many small galaxies to fewer, larger systems. Eventually, in the far future, galaxy mergers may lead to a universe dominated by a small number of extremely large, elliptical galaxies. In the distant future, after all major galaxy mergers have taken place, the universe may become a much quieter and more isolated place. Star formation will slow as gas is consumed or expelled, and galaxies will age and fade. Black holes will dominate the centers of galaxies, slowly growing as they consume surrounding matter. Eventually, even these processes will come to an end as the universe continues to expand and cool. Galaxy collisions and mergers represent one of the most important forces shaping the structure of the cosmos. They drive the formation of new stars, the growth of galaxies, and the evolution of large-scale cosmic structures. They connect the past, present, and future of the universe through a continuous cycle of interaction and transformation. In the grand story of the cosmos, galaxy collisions are not just destructive events. They are creative forces that build complexity from simplicity, order from chaos, and structure from motion. They remind us that the universe is not static, but constantly evolving, shaped by gravity and time into ever-changing forms.